So we are going to be looking at hyperbolic identities today, and these hyperbolic identities look familiar but different. Sometimes they look exactly the same, sometimes they look slightly the same as their trigonometric counterparts that we have. So this is an identity for hyperbolic ones. Normally, we would say sine squared plus cos squared is 1, or cos squared plus sine squared equals 1. But the identity that we have for the hyperbolic functions is cosh squared x minus sine squared x is 1. And we're going to prove this by using the definitions of sine and cosh. When I say use the definitions, I mean use their exponential definitions to try and do this as a proof. So I'm going to actually work out what cosh squared x minus sine squared x is. I'm going to keep working that out as I go down the page, and I'm hoping it's going to end up with 1. So we know that cosh squared x is going to be a half e to the x plus e to the minus x all squared minus a half e to the x minus e to the minus x all squared. Okay, so probably the best thing is just to deal with the half being squared first and writing it as a quarter, and then to start squaring this. So anyone think they can tell me what this would square to? Shahan?
So would it be e2x?
Yep, e to the 2x.
Minus 2.
It's going to be a plus because of the plus here.
Okay. Just plus 1
Plus 2, because there's going to be 2 of them. When you do the e to the x times the e to the minus x, you get e to the 0, but you're going to have that twice. So you're going to have a plus 2. And then at the end, we will have an e to the minus 2x. If this is difficult, because I know you can do it when it's just like x plus y or something, what you might just find useful is writing at the beginning of this topic. You might just find it useful to just somewhere else on your page just to write them out and to just take it a bit more slowly. There's no harm at the beginning of a topic in taking it slowly. The reason I don't always take it slowly is to show you that you can do it without doing it slowly, if that makes sense. Like, I want you to raise the bar on what you think it could be like, okay? Now this next bit, we are going to subtract a quarter of this thing, which is being squared. So how is this one going to be different? Yeah, so it's going to be e to the 2x minus 2 plus e to the minus 2x, like this. And then I'm going to expand all the brackets. So I have a quarter e to the 2x plus a half plus a quarter e to the minus 2x minus a quarter e to the 2x plus a half minus a quarter e to the minus 2x. So everything cancels out apart from the halves. This cancels with this cancels with this, so we end up with 1. So cosh squared x minus sine squared x is 1. Now it's nice because the identity is familiar, but it's annoying because the identity is not the same. So later on in today's lesson, we're going to learn a rule that will help us to learn all of the hyperbolic trigonometric identities just by looking at the trig identity. We're going to be able to find a shortcut that will tell us what the hyperbolic version is from the trigonometric version. We won't have to try and work out every single one individually. Okay? So I want to know what else we could prove. We know now that cosh squared x minus sine squared x is equal to 1. And in the trigonometric version of this, what did we call the trigonometric version of this identity? The Pythagorean identity. So what other things do you think we could create here? Yeah, we can create the alternative Pythagorean ones. How did we create those in trig, and how will we create them in this, Sam? Okay. Good, so I'm going to do one version where I divide everything by cosh squared x to get a new identity, and I'm going to do a different one, which I guess I really should do in a different colour. I'm going to do these, I'll do this one in red. So I'll divide everything by cosh squared x for one of them, and then I guess one I'll do in black, I'm going to divide them all by shine squared x, and I'll come up with some new identities, okay? So first of all, I'm going to divide everything here by cosh. If I divide cosh squared by cosh squared, I will get 1. If I do shine squared divided by cosh squared, I will get tan squared. And if I do 1 divided by cosh squared, I get sech squared x. Okay? Now, what does the trig one normally look like? What's the trig one? Yeah, it's normally 1 plus tan squared equals sec squared, but we've now got 1 minus tan squared equals sech squared. Okay, so similar, but a little twist. And now we're going to divide everything by shine squared. So what is cosh squared divided by shine squared? Coth squared. So we're going to have coth squared x. And shine squared divided by shine squared is minus 1. And 1 divided by shine squared is cosech squared x. Okay, so we've got some new identities that are here as well. Again, this one looks familiar, but it's different as well. The things that I find that are familiar about them is that the tan and the tan squared both have a 1 on their side, and the tan and the tan are both associated with either the sec or the sech squared. But there's a difference to do with negation somewhere, and it's not clear what that's going to be, but there is a difference of negation. Then we've also got for this one here the same kind of properties. We've got cot and coth and cosec and cosech. And we've also got that the cot is the one that's with 1, but there's something that's happened with negation that we'll be aware of and how we can figure that out in the future. So we've now got more identities. Personally, I memorize this identity. I use this one a lot in hyperbolics. These ones I don't memorize. These ones I think a little bit carefully about, either by deriving it from here. My brain just kind of runs out of space. I kind of feel like you can overload your brain with too much information, and I'm trying to advise you on what things I want you to commit to memory. I don't know if this needs to be committed to memory. This one does, the blue one, okay? So we're going to keep going. We're going to do some more identity proving. This one, is this one the same as the trigonometric one, or is this one different at all? This one is exactly the same. So we're starting to see why hyperbolics are actually called trigonometric hyperbolics, because they've got a lot of similar properties between them. So we're going to prove the following identity using the definitions. If they ever say using the definitions of shine and cosh, obviously they're wanting us to use the exponential definitions that we've got there. So this is the same as the trig one, apart from it's been made hyperbolic, and we're going to try and work out what this is going to be. So we're going to do the shine of a plus b from the definitions. So what would the shine of a plus b look like from the definitions? It would be a half e to the a plus b
minus brackets a plus b.
Good. And so we need to start playing around with this to try and see how we can manipulate it some further, how we can take this a bit further. So I'm going to have a half. What is e to the a plus b? How else could I write e to the a? E to the a, e to the b. And this is going to be subtracting e to the minus a minus b. So I'm going to just keep going for a second. That's going to be e to the a, e to the b, minus e to the minus a multiplied by e to the minus b, like this. Now I have to remember what to do next.
Would you make it into 1 over e to the
Yes, I think that's something that we should do. I think we should...
You can just make it e to the a, e to the b minus 1 over e to the a, e to the b.
We need to keep them as separated things. Let's try that. And then I might have to quickly have a look as a bit of a reminder, because... So it's the same as this.
And then isn't that the no, but you can't use the Z function, can you?
No. Let me just remind myself.
It's going to be... What is it?
Oh, of course. This was not a good side to start from. What do I usually say is the better thing to do when you've got a proof? Go from the messy side and try and make it go to the unmessier side. So this was perhaps a bit of a waste of our time, because really this is where all the complexity is. And I didn't even take my own advice, which is that if we have something that's complex, it's much better to go from something that is complex to something that is simple. Because we've kind of got to this stage, and what we're actually trying to do here is like pull it apart, and we don't really know how to pull it apart. So I'm sorry if I've probably wasted some of your time and space on your page. We're not going to start from the left-hand side in this case. We get a bit stuck. So we're going to start with this instead. We're going to start instead with shine A cosh B plus cosh A shine B. We're going to work on that side instead. And I'm actually going to start my working out down here because I think I'm going to run out of a bit of space, okay? So I've got shine A is going to be a half e to the A minus e to the minus A, and cosh B is e to the B plus e to the minus B. And I'm going to add on cosh A, which is a half e to the A plus e to the minus A, multiplied by a half e to the B minus e to the minus B. This will work out very quick now. Well, not very quick, but quicker than what we were trying to do. So I've literally just put all the substitutions in for these bits that I've got.
That's scary maths.
It is pretty scary maths that we're doing at the moment, yeah.
I feel a bit like a child asking you this because you're going to be like, we don't use those. Do you have any graph paper?
There might be some graph paper in the cupboard.
Thank you.
The only place it would be is just on the left-hand side, unless there's something here.
Oh, there's some here.
There's some there, great. Okay, so let's evaluate the first terms that we've got here. We've got a quarter from these halves, like this, and then I'm also going to expand these double brackets that I've got here, okay? So expanding them really carefully, I'm going to have an e to the A, e to the b. Should I just do it as an a plus b? Are you okay for me to go straight to adding the powers because they're being multiplied? So we're going to go to e to the a plus b. Then I'm going to have this one multiplied by this one, which is going to be a plus e to the a minus b. Then I'm going to do this one times this one, which is going to be minus e to the minus a plus b. And then this one times this one is minus e to the minus a minus b. Okay? And I'm going to do the same on the next part. So I'm going to have a quarter e to the a plus b minus e to the a minus b plus e to the minus a plus b and minus e to the minus a minus b. And now you can see why we needed to have these definitions memorized, because you want to just be able to use them straight away. Now, if you want, you can fully expand things, or you can be smart and do some cancelling at this stage, because you can recognize that everything has a quarter with it. Now, I think when I was your age, I probably would have expanded everything just to be really, really careful. But also, it's kind of obvious to see if I've got this multiplied by a quarter and this multiplied by a quarter, there's going to be some pretty easy cancellings that can happen here. Can you spot any of the things that cancel? Yeah, this e to the a minus b is being added, and then over here it's being subtracted. And did you say another one? Yeah, this, a minus a plus b for the power, is going to cancel. So we're just left at this stage that we've got here. Okay? If that was too quick for any of you, you can always multiply and then see, multiply them all out and then see how they cancel. So I'm going to just expand now. I have a quarter e to the a plus b minus a quarter e to the minus a minus b plus a quarter e to the a plus b minus a quarter e to the minus a minus b, which simplifies to a half e to the a plus b minus a half e to the minus a minus b, and you can see what's happening, hopefully. I can then factorize out the half, and I have e to the a plus b minus, what do you think I should write the power now for the second one?
A plus B, so it's going to be minus by 2.
I'm going to do minus a plus b, like this, which is the definition of sign of a plus b. So definitely made sense to go from the right-hand side to the left-hand side in this case. I foolishly started going from the left-hand side to the right-hand side, which was never going to work. It was too simple, the thing we had. We needed to go from the complex to the simple that we had. So the addition formula for sine is the same as the addition formula for sine, which means the double angle formula will also be the same because of what we looked at the beginning with double angle formulae, okay? So, yep, I want you to just have a go at starting to do the next one yourself, okay? Have a go at starting to do the next one yourself. And again, I would recommend working on the right-hand side for this question, okay? No, because of the squaring. Yep. So you're going to have it as this instead. It's going to be 2 multiplied by. This one's not as bad as the other one, I don't think. Yeah, I agree. So we've proven a different identity. We've proven that cosh 2a is 1 plus 2 sine squared a. But does anybody remember, just from half an hour ago when we looked at the double angle ones from trigonometry, does anybody remember what cos of 2a is, the sine squared version of it? Have a look. Did you write it down? If you didn't write it down, it doesn't matter, but what the double angle formula is from trigonometry. It's 1 minus 2 sine squared a. So you've got your hyperbolic one and your trigonometric one. They're nearly the same, but there's a negation that's happened. And so in a minute, we're going to try and figure out where is that negation coming from and like how can we deal with that, okay? So the way that these things are different, well, actually, I'm going to separate this. I'll put this in a different video.